I want to start by thanking both Lydia and Nuria and also all the student volunteers for putting together such a wonderful school. In fact, I was a student at an older version of this school back in 2019, and it was sort of one of my first points of contact with foundations of physics and foundations of quantum physics. So this really feels like a full circle moment, and I hope that I can share some of the things that I've learned in the last years with you. I have shared these handwritten notes with you on Discord in case you have a digital tablet and you want to take notes. Otherwise, I think I encourage you to maybe not spend all of your time writing down and maybe just listening, and then you can trust that you will have the notes. Also, please interrupt me if you cannot read something. That would be a really stupid reason to not understand what's going on, or also if something's not clear. Right, so in this lecture, I will build on the introduction that Flaminia has given in the previous two lectures on sort of frameworks of quantum reference frames. And in particular, I will try to show to you how we can go beyond what we call ideal quantum reference frames and construct non-ideal ones. And I will explain what I mean by this in more detail. In fact, the plan is that first I will define what I mean precisely by an ideal quantum reference frames, how we can go beyond them, and maybe what obstacles that we encounter on the way to doing that. Then I will use the perspective neutral approach, which we've already heard about now, to show you how we can treat non-ideal quantum reference frames in that approach. In particular, we will build so-called complete quantum reference frames using coherent state systems. We will see how to make sense of relative states, relational observables, and so on. And then we will see that actually the perspective neutral approach and the perspectival or foundational approach that Flaminia presented as well are mathematically equivalent precisely in the case of ideal quantum reference frames, which is, I guess, another justification for why it is fine to start in this perspective of one quantum system and directly transform to the perspective of another system without having to go via this perspective neutral, God's eye view from nowhere. Then, in the interest of time, I will not present further types of non-ideal frames in full detail, but I will try to give you an overview, sort of a classification of other types of non-ideal frames, in case you're interested in exploring this more. Then I will most likely not have time to show you a very explicit example of these non-ideal frames with the coherent state systems, but I did include it in the notes. This is work that we did during a project, and I think it's quite pedagogical to go through sort of one of the most simplest example, which is here the group of S3, which is a permutation group with 3 elements. So if you're interested, you can have a look at this. Okay, so let us start with what precisely I mean with an ideal quantum reference frame. So we've seen so far the Galilean group and also the translation group, but I want to point out here that we can treat these quantum reference frames for any symmetry group or gauge group that we want. And in fact, there was the question already in the previous lecture, how general can we go? And in fact, what we can do is we pick our symmetry group G, and either we pick it as finite, that's sort of mathematically the easiest case, or if it's a continuous group, then it should be a locally compact Lie symmetry group. Locally compact just means that I can pick any point in the space and its neighborhood is compact. Non-mathematically speaking, this means most groups are fine, and in particular, the translation group with the real line is a locally compact group. Okay, so by an ideal quantum reference frame, I mean very abstractly some quantum system which I take to carry the regular representation of the group. All this means is that the group is acting on the states in the Hilbert space, where the states in the Hilbert space are marked by the group itself. What that means, or what that implies, is that the Hilbert space that I use to represent the system is L2 of G. These are the square integral functions over the symmetry group, which means that I have here an equivariant map from any group element in the group, and I can map it to some ket in the Hilbert space ket G. And in particular, if the Hilbert space is L2 of G, it means that for every group element, I can find a new independent orthogonal direction in the Hilbert space. So that means that any 2 different group elements, for example, any 2 different positions, are assigned orthogonal, perfectly distinguishable quantum states. So we have this condition right here, that the overlap between 2 such states, G and G dash, is 0 if G and G dash are not the same. Okay, if we have this mathematical structure, then we can apply so-called quantum-controlled symmetry group transformations. So to give you a concrete example, we can take the one-dimensional translation group, so we have some particles or systems, A, B, and C, on the real line. And I want to consider A and C as my ideal frames, so they're both described by L2 of R. That's their state space. And I'm also describing quantum system B. I'm not making further assumptions, except that it also transforms under the symmetry group G, but it just needs to be some unitary representation. Okay, and then we already saw in the previous lectures that for the translation group case, the quantum operator which transforms between the perspective of A and the perspective of C can be written as this parity swap operator between A and C, and this exponential operator here, which controls on the position of the new frame and translates accordingly the other systems. We can write this operator here also more explicitly in the form of an integral over all positions. And you see here, this is the form that it takes. So it will run over the entire real line until it encounters a position where the new reference frame is. So that could be this position here or this position here. And for each branch of this quantum superposition state, it will pick up an x, it will send the original reference frame to minus x, and then it will also move all other systems accordingly. So we can see this in this picture right here. In the branch in which C is in this left position here, it will map everything to, this one will be mapped to minus x1, and then we have this wave packet here. And then for the other branch where C is in x2, we also have a translation by minus x2. So this is what I mean by quantum controlled. Okay? We're controlling on the position, or generally the group configuration of the new frame, and transforming accordingly. Now, very importantly, okay, before I go there, we can do this for general groups. So as long as they're locally compact, you can generalize this intuition from this paper right here for any locally compact symmetry group, and you just, again, integrate over the entire group. You pick up on G for system C. You send A to the inverse group element, so that's what this parity swap here does. And then you also move all other systems B, C, D, E, however many you have, also you transform them with G inverse. Okay. My point here is this works exactly if these ket G's form an orthonormal basis of the Hilbert space. So if our Hilbert space is L2 of G, because then these are orthogonal and they're really going to pick up on each branch of the superposition separately. Now we can ask, what happens if we loosen this assumption? What happens if the ket G's, so the states associated to different symmetry group elements, have overlap? Well, a first result that I briefly want to talk about is that the quantum reference frame transformations of the perspectival approach or foundational approach for any symmetry group are unitary if and only if they carry the unitary representation. So if and only if the frame has Hilbert space L2 of G. Okay? In this case, our frame orientation states, as we call them, are orthogonal, and then this logic here works that this picks up states and they're orthogonal, and we can make sense of this logic. Now, what this means is that quantum reference frame changes are unitary only if both frames, the old frame and the new frame, are ideal frames in the sense that G, the group, acts regularly on itself, and these states, psi of G, are perfectly distinguishable. Okay. In the interest of time, I will not go through this proof. It's really not that difficult. You just take the overlap of two states, and you show that the overlap is only conserved under the quantum reference frame transformation if the states are orthogonal, and by that you prove that the transformation is unitary. Okay, so you can look at this here if you're interested, but really there's nothing very technical in this proof. So what we can conclude is that if we want to construct unitary frame changes, and you can ask why, between non-ideal frames, then we cannot straightforwardly do this on the states that we have seen so far, which are kinematical states. Okay. Now, why would we want frame changes to be unitary? Well, in general, we want that no matter what perspective I take on, even if it's the perspective of a quantum system, I want the probability of a detector to click or of an event to happen, I want it to be the same in all perspectives. I want consistency between different quantum frame perspectives. Now, we can discuss if there are situations in quantum theory where maybe this assumption should break down, but as long as we have quantum systems sort of on the same level and well-behaved situations, this is something that we want. Okay. Now, one way, I'm not saying the only way, of allowing for unitary frame changes, even between quantum reference frames that don't have Hilbert space L2 of G is that we have to remove some of the gauge-induced redundancy. So if two different frame orientation states still overlap in a way, it shows us that there is still some leftover redundancy, which we need to get rid of. And one way to do this is to go to the perspective neutral approach, and we will see now how this works. So as a reference, I will use this paper right here, in which we constructed these non-ideal quantum reference frames for a couple of different cases. So in general now, we will take a quantum reference frame to be a quantum system which simply carries some unitary representation of the symmetry group G, okay, not necessarily the regular one. And as a consequence, different frame orientations can be assigned overlapping non-orthogonal coherent states. So what I want you to keep in mind from now on is that when I write ket G and ket G dash, I will not mark that they're not orthogonal. So in the paper, we actually have some notation to make sure people keep in mind these are now overlapping states. I will not do this here because the notation becomes a bit too cumbersome. Just keep in mind that these G's now, or later even if I were to write ket X, what I really mean is some coherent state which can have overlap with some neighboring position state. Okay, so let's see how we can construct these complete quantum reference frames. So I will consider from now on not systems A, B, and C, but I will call them reference system R and the system of interest that I'm describing S. And one important assumption that we will always take to be true is that these two systems transform under a unitary tensor product representation of this Lie symmetry group G, so that G acts on R and S in the same way. If there is G acting on R, there is also G acting on S. This here should be an S. Okay. So you see there's already some tensor product structure here, and let me just say that in full quantum gravity, this is an assumption that we have to rethink again, because sometimes this doesn't work in full quantum gravity theories. Okay, what we can now do is define globally invariant states. These are physical states living in the physical Hilbert space. So this is something that Flaminia also talked about already. So these are any states in the kinematical Hilbert space which don't transform at all, even if I apply this unitary representation with G. And then these physical states can be written either as exactly those states which vanish under the constraint. So in the previous lecture, this was this delta of p hat. All the physical states vanished under applying this delta operator. But if you don't want to talk about constraints, you can also formulate this in a group and representation theory language. So this is equivalent to saying that there is this improper projector, which projects from the kinematical to the physical Hilbert space. So we take some kinematical state. This is really anything you can think of. I can be God, or we call her sometimes Eve, and she prepares some state. And then using this improper projector, we go to the physical state. What this projector does is it produces a highly entangled version of the kinematical state. So you see here that we take our representation, U, R, S. In the translation case, this really means, let me translate reference frame and system by some amount, and now I integrate or I sum over all possible distances by which I could translate this. So you can think that this kinematical state is just my frame being in some position and my system being in some position, maybe some superposition states, and now I map this to the very entangled sum of all the translated versions of this state. Okay? This is so that we increase sort of the redundancy. We have all sorts of gauge-transformed copies in this state here. Okay, and this is what is called the coherent group averaging. Coherent because a pure state here will still be mapped to a pure state here. In the quantum information approach that we've also heard about, we're not applying this operator, we're applying this to the density matrix. And so then it's mapped to a mixed state where we really have loss of information.
Excuse me?
Yes?
The state is entangled with respect to what partition?
With respect to the kinematical tensor product partition. So we have R tensor S.
Yes.
And even if I start with a product state where R and S are not correlated in any way, this state will highly entangle R and S.
You mean the projector? The projection will highly entangle?
Yes.
But this projection is a stochastic local operation between R and S. How can it be not monotonous? Like, how can it increase entanglement if it's in a sense like classical and local? Classical and local, sorry.
It's not classical and local because it's URS. So
URS it respects the tensor structure.
Right, but I'm mapping a state, which is, for instance, cat x, cat y, and I'm mapping it to a sum of x plus a, y plus a for all possible a. It's what we would call a fake superposition. So there is entanglement in the kinematical tensor product structure.
Okay.
And you can argue that this tensor product structure is not the right one for the physical Hilbert space, but maybe it helps to say that this is an improper projector. Like this will not map to normalized states.
Well, maybe we'll talk about
Yeah, we can come back to it. Okay, good. So now we have this physical state living in this perspective neutral Hilbert space, this physical Hilbert space. Now we will assume that we can find a so-called coherent state system. Now you must have heard of coherent states maybe in some quantum optics lecture. Here these are generalized coherent states, of which the coherent states in quantum optics are one instance. But really in general it just means that I have my group structure. So I have some state G, this can have some spread, whatever you want, in the Hilbert space of your choice, and I have my representation UR of the reference frame acting on it. Okay? And importantly, we assume that this representation acts transitively. So what this means is that I will start by choosing one state. I call this the seed state because that's what I planned. It's E. It lives in the Hilbert space. And E here marks the trivial or unit element of the group. And then I can generate all other states in my Hilbert space that I will name G by letting UR of G act on it. And if it's transitive, it means I can get to any other element in the Hilbert space uniquely. Okay, so then GG dash is generated by letting G act on G dash. Okay. Now, so you can here keep in mind this picture that if you have some let's say, cyclic group and you start with some very peaked state and now you generate all the other peaked states. You could also start with a much broader state or some state of a very weird shape and generate all the others. Now, I cannot do this in whatever way I want. There are some restrictions in this construction. And the important one is that the way in which I choose this seed state, it has to give rise to a resolution of the identity. Resolution of the identity just means that if I sum over all the projectors GG, cat bra, I have to get some multiple of the identity. This is a sort of, I have to impose this so that later I can make sense of the probabilities that I get from my states and my observables. So if we are working not with locally compact but with compact groups, then actually I can tell you that this constant here is just 1 over the dimension of the frame. Okay, and this allows for the treatment of non-ideal frames. Okay, now this coherent state system allows me to define a POVM, and in particular a POVM that transforms very nicely. So the elements of this POVM will just be marked by these elements here. So I can choose any Borel set over the group, depending on how precise or how broad I want to measure my frame later on. And then they will look like this. And if I choose this coherent state system in this way, then I will make sure that this is a normalized POVM, and it also transforms in a nice way, so that if I transform this Borel set on the group, I get a according transformation of my POVM elements. Okay. Now, if I have this, then I can now write all physical states as an integral over the entire group, where I have some state on the reference frame and then the according sort of relative state on my system. Okay. And in fact, how do I now make sense of the relative state? So what is the state of the system relative to the frame? Well, I can say that if we apply this POVM and we measure some orientation or state G on the reference frame, then the corresponding relational state on the system is exactly the one where I take the physical state, which now contains all these copies, all these gauge transformed copies of my kinematical state, and I pick exactly the one which overlaps here with G. Okay? This is what we call the Schrödinger reduction map. So this is sort of related to Flaminia's trivialization map, but it works slightly differently. And importantly, we have to keep in mind here that now we're not conditioning on some orthogonal cat x, which doesn't have overlap with any other position. This conditioning here will pick up on other copies of the state that have overlap with this G, but that don't actually correspond to the kinematical state where the frame was G. Okay, does that make sense? Good. Okay, so these are sort of the states that we would assign to the system after we measure and we say, my clock shows time 12 p.m., therefore I infer that the system is now in this state. Okay? I'm mentioning here the clock because this all goes back to, or is inspired by the Page-Wouters formalism, where we try to make sense of sort of the state of the universe relative to some clock, and we're entangling the clock with all the rest, and then we're looking at the clock and we make sense of what we can see and observe on our other systems. Okay, I do want to put a sort of word of caution here that you have to normalize these states, and this works very well for compact groups and not so well for locally compact groups. Okay. Now, one nice feature of these relative states that we get, yes?
About the normalization.
Yeah.
If you have a post-measurement state, shouldn't you normalize it with the probability that you measure G? So you have to define the probability. So in a way, it's the post. This
Okay.
reduced state is the probability times the post-measurement state. I think.
So you can re-normalize, not the scary renormalize, but the normal renormalize, the state after applying this conditioning by, in the case of compact groups, all you need to do is multiply with this dimension of the frame.
But I was thinking about the post-measurement state, the probability. Maybe I'm misunderstanding.
So I know what you're getting at, because normally in Page-Wouters we have this formula where we divide by the probability of getting this particular outcome. I think this is taken care of in the way that we construct this coherent state system, that there are some conditions on this E, and from this that this takes a nice form. I can't rederive it now on the spot, but
Okay, so
yeah.
you absorb it somewhere.
Yeah, yeah. Okay. Good. Now these conditional or relational states have or satisfy a very important property, and that is that they still transform in the way that they did before. We have this representation of the group that our system carries, this US, and we see now that even though we applied this sort of reduction procedure, and it's not trivial in the case of non-ideal frames because of this overlap, we still have the nice property that if I have my system conditioned on my frame showing some particular time, then if I translate by some other time, G dash or T dash, I really get the corresponding conditional state as if though I had immediately conditioned on G dash G. So this still respects the representation structure, so we're still good. Our system, even relationally, still transforms under the group. Okay, so this is an important thing to check. Okay, now, importantly, because we defined this Schrödinger reduction map here to act on the physical states and not the kinematical states, we can now show that this map is invertible, so that I can go back and forth between the physical Hilbert space and the perspective. And in fact, here I need to define the inverse, and I do this by sort of before we were conditioning, so now I'm adding the G here of the frame, and then I again apply this physical projector so that I go back to my physical Hilbert space. Okay. And then we get to this triangle picture, which we already saw in the previous lecture, but now it is generalized to all ideal and also the non-ideal complete quantum reference frames. So just to recapitulate what is the picture we're working with, we have some kinematical structure up here. And now, because I want to get to making sense of changing between different frames, you see here that actually now I'm no longer talking about R and S, but I'm adding two frame systems. So I have R1 and R2 and S. Okay, I just added yet another tensor product factor. Then from here, I can go down with my physical projector or imposing the constraint, depending on what you prefer, to the physical Hilbert space. So this contains all the states that are invariant under my symmetry group acting. It contains all the copies in an entangled manner. And now I can choose whether to reduce to the perspective of R1 or of R2. So here I reduce to the perspective of R1 being in G1. This could be something like my first clock shows time T1, and then I get to this Hilbert space. Or I reduce for my second clock to show some other time T2, and then I get to this Hilbert space. Okay. And then so on this level down here, we're really now in different quantum perspectives. So this is what the perspectival, the foundational approach, was talking about. So now we would hope that we can still go from here to here. And as we even saw before, we can just compose this map here, going up again and then down again. And then this should define us unambiguously how we go from here to here. And that's exactly what we do here. We undo RS, R1, G1. And we can do that because it's invertible, and that's not obvious. And then we go down into this perspective here. So if we just want to perform a quantum coordinate change or a quantum reference frame change, we define it as the composition of these two maps, and it will map some relational states of my remaining systems RJS, given that my frame is in GI, to the relational state of RIS, given that my frame is GJ. Okay. Now, I can show you here that this already looks very similar to the foundational or perspectival approach. Actually, we will see this later. So let us write this out here more explicitly, because this is still very abstract. So if I want to change from my frame Ri to my frame Rj, where Ri is in the configuration Gi and Rj is in Gj, then all I have to do is I have to pick up on this group element on my Rj and map it over here into this one, and I also have to transform my system. So you see that this is a very abstract generalization of this other transformation, where we also picked up on some position of the first reference frame and then mapped it to the position of the other reference frame. Okay. We will not go through this proof, but it's very, very short. Okay. So this was for the states, the relative or relational or conditional states, but we can also talk about observables here. So if I want to measure or make sense of an observable Fs on my system of interest, I can take any arbitrary system observable. This will live here. Then the first thing that I need to do is I need to couple it to my reference frame. I need to make them talk to each other. So what I do is I take this Fs and I couple it to my reference frame showing orientation G or my clock showing orientation T. So I couple it to this projector right here. And this is a non-invariant description of this system property, conditional on my frame being in orientation G. Now, how do I make this not non-invariant? Well, I apply this G-twirl. So this G-twirl here, I can show that it's, at least on the constraint surface, the same as applying this physical projector. So what this looks like is, again, I average over my entire group, and I apply the same element G dash both on my frame and on my system. So this is something like I take some observable on my system, I make sense of it when my clock is showing time 12, and now I average over the clock showing any other time, but also my system observable is time evolving with it. And so in this sense, I encode the observable of the system in an invariant way conditioned on the clock. Okay? And in this sense, this is a covariant POVM construction. I can now measure my clock and know what observable this corresponds to on my system. This is very abstract, so let's try to look at one example. If, again, we take the translation group, so we just have the real line, and I have some reference frame that is ideal in this case, L2 of R, and some system that is also L2 of R. Then now I can take the position operators of my frame and of my system. So Fs up here is now Qs. Then, to construct the relational observable that encodes where S is, the position of S, conditioned on my frame being in some position Y, what I do is I take Qs. So now I'm taking this line here, and I'm just applying it to the translation case. So I will average over some position X. My frame will be in XX. And then I translate my system observable by x minus y. And if you go through some integration variable changes, what you find here is that the observable that comes out when you put in Qs is precisely Qs minus Qr plus y. Okay, now normally we would put our reference frame in the origin in position 0. So if you put y to 0, you see that it's precisely this relative position operator. Okay, so this is the way in which we map absolute observables into relative observables. But we can also make sense of our clock showing some arbitrary time that we want, or the particle, our reference particle, being in any other position, y. Okay. Okay, any questions up to here? Yes?
I only wanted to ask, It's on? No, it's on. Thank you. No, I wanted to ask because you define the ideality depending on the overlapping or the orthogonality of the states generated by the group on the elementary state E. Okay. So, okay, then the importance in this context is that these states G are states of the reference frame.
Yes.
And then you say that the reference frame is not ideal because there isn't this the orthogonality. Okay, then I would say, so the orthogonality of these states depends on the group which generates them, right? Because the states G completely depends on the UG that you define.
I would say the representation, in fact, not the group.
Okay, the state G that you get from E depends on the representation of the group and on the group also. On the representation. Okay, yes. Both the representation of the group and the group. Okay, and I would say that, for example, maybe for an angle, that group would be the rotation group. For a translation, for a position, that would be the translation group. Okay, then my question is, so the ideality or non-ideality of a reference frame depends on the characteristic property that we need to, the characteristic property we are describing the system with and the reference frame with. In another way, if we are describing the reference frame, if the property we are interested in of the reference frame is position, we have ideal reference frames. If the property we are interested in is I don't know, angle, no, we haven't, because the group generates non-orthogonal. No, I didn't get.
No.
Okay.
So, but this was very helpful. So, let's say you're interested in position, then your group is the translation group, which is R acting with addition. Okay? You haven't specified your representation, so you haven't specified the vector space on which it acts. What I'm trying to say is that it's precisely the representation which decides whether it's going to be an ideal or a non-ideal frame. Okay? If you have a Hilbert space that's big enough to have orthogonal states for every single angle or position or momentum or Lorentz frame orientation, whatever, then it's an ideal frame for any group, L2 of G. Okay? If you have let's go very extreme, you have a qubit, it only has 2 degrees of freedom, but you want to encode position. How do you do it? In fact, in this very first paper, we tried to do this, and we said, okay, let's be pragmatic and say if the position is bigger than 0, then it's 1, and if it's smaller than 0, it's 0. So it's a very coarse-grained way of doing it. What I'm trying to argue here is it's the size of the Hilbert space and the properties of the representation that the frame carries that fully determines how good or bad of a frame it is. Okay? In fact, in this paper right here, we actually ask precisely this question. Can we choose a seed state E, so a very peaked one or a very broad one, and make the quality of the frame better or worse? And I think we would all intuitively agree that if you pick a very peaked state, as opposed to a very coherent one, this should be a better frame. Turns out this intuition is wrong. It doesn't matter how you choose the seed state, it matters what the representation is. And in the end, one very important property of the representation is how big is the Hilbert space. If your frame has a big Hilbert space, you will have a lot of resolution to make sense of the different orientation states. And then more stuff about what irreps does your representation decompose into and so on. And you get a very beautiful group representation theoretic expression, the multiplicities of this irrep matters and so on. But it does not matter how you choose this one right here, because you're going to average over it anyway. Okay? So the properties that matter are all encoded in the representation. So if that's what you take away from this, I'm happy.
Okay. No, that's important, because I thought it was depending only on the group. No, only one last thing. So I could think, I don't know, if I wanted to once more try to understand the relative angle with respect to one reference frame, what would be the right choice of doesn't matter.
Yeah, L2 of SO3.
Okay. So the point is that, because the first thing that came to my mind, the angle of the, which is like L2 of onto pi maybe.
Yeah, to give another example, when we thought of this qubit example to encode, like we thought of a ball and some point or some particle on the ball, right? Like you think of the Bloch sphere. You can either try to make sense of this as a qubit, but then you only have a two-dimensional Hilbert space to encode where on the Bloch ball that particle would be. That would be a terribly bad frame because of the size of the Hilbert space. But if you take L2 of S2, then it's fine, because now you have an orthogonal state for each individual position on the ball. So it's really the size or the Hilbert space, and by that the choice of representation that tells you whether it's a good frame or a bad frame, whether it can resolve some configurations better than the others. Does that make sense?
Yeah, I missed.
There was another question there.
Yeah. So, is it basically about the faithfulness of your representation?
Very good. We're going to get to this because in the classification that I'm going to show, I'm going to make a distinction between whether the action of the group is just transitive or also free and regular, and what happens if not. But you can make a beautiful classification if you give up on some properties of the action of the group.
Okay, that's pretty cool. Cheers.
Yeah. You can give it back.
I was surprised when it turned out that this R operator, the reduction operator, was invertible, because kind of my intuition was that it picks out some orientation, and so you lose some information. And so, yeah, is there some intuition why this logic is wrong?
Very good. Is it okay if I get to this and then, because it's part of, we want to understand exactly why does this suddenly work when before we proved that it didn't work. And I will come back to this, and if you're not satisfied with the response, we will talk about it again.
Perfect.
Yes.
Yeah. Would you say, based on your previous answer, would you say that the representation also defines the system of coherent states, G?
Yeah.
Yeah.
That's precisely what I'm saying.
Yeah.
The system of coherent states is almost entirely determined by the properties of the representation. It does depend on the seed state. Okay, I didn't say before that no matter what state you choose here, the CSS is going to be the same, but the figures of merit that we looked at for what we think encodes whether it's a good frame or a bad frame, none of them depended in any way on whether we chose some very peaked seed state or a very broad one. Okay. Also, I have to say that this resolution of the identity massively restricts your choice of CSS. So if that wasn't the case, of course, many things could happen. But in a way, this already really restricts what.
Yeah, that's what I want to hear, because the resolution of identity, I mean, it's not completely dependent on the representation. It also depends on the coherent state, so that you can have the resolution of the
course,
identity.
Exactly.
Right?
For one and the same representation, we do this, I think, in the paper somewhere, in this paper right here. We choose two different E's, and then we show, as in, one choice of E can satisfy this and another cannot. And even if both do, there will still be differences. But it turns out that for the figures of merit that make sense, that you can motivate well physically, this doesn't matter.
Okay, thanks.
Yeah. Okay, any more questions? Good. Okay, I realize that this is quite technical. This is why very few people read this paper, but I'm trying to do my best here. And so I think questions are actually better than trying to get through all of the material. Okay, so we saw how we can construct these observables as well and make sense of also position operators relative to the frame and so on. Okay, I think we can skip this part and just go to the quantum coordinate changes, because we saw how we can make sense of, or how we can transform the quantum state of my system relative to frame Ri to the quantum state of the system relative to frame Rj. And all I want to say here is we can obviously do the same for observables as well. So if I start with an observable that I constructed using this G-twirling and the adding, and I have my relational Dirac observable that I call f of Rj and S relative to my frame Ri being an orientation Gi, then I can apply this same map from before, just on both sides here. I do believe there's a dagger missing here. And I can get my other observable here, or rather, I map from here to here, obviously. So from one system observable physical algebra to the other one. Okay. Now, to get to what I was saying at the beginning, we can now ask in what cases does the perspective-neutral approach reduce to that of the perspectival or foundational approach, and vice versa? When are they the same? Because in the perspective-neutral approach, we have this triangle picture, and we made sense before of these reduced perspectives as being precisely the starting point of the perspectival or foundational approach, and us just mapping back and forth between different quantum perspectives. And it turns out that it's precisely for frames that transform under the symmetry group with the regular representation, so precisely the frames that have Hilbert space L2 of G, that the two are equivalent. And in fact, if I choose my frame orientations of my frames I and J to be precisely the trivial group element, so that corresponds to my frame is itself in position 0, or my clock is showing some time 0 that I agreed on, then I get exactly this frame transformation that we had before. So we would transform a state from here to here. Okay. And you can show that this more general transformation from above precisely reduces to this one right here, which is the normal quantum reference frame transformation. So we can conclude that the perspectival and the perspective-neutral approaches are equivalent for ideal quantum reference frames. So if we have L2 of G frames with orthogonal frame orientation states. Okay. Now, we can discuss, and that was your question, why is that the case? Why is it that before we could prove that there does not exist a unitary frame change if I want to change from, let's say, an ideal frame into a non-ideal frame, or even between two non-ideal frames, my frame change operator would not be unitary because these frame orientation states overlap. How is it that now they still overlap, but somehow we managed for the Schrödinger reduction map to be invertible, and therefore this frame change to be unitary? Okay, and the reason for this is that these frame change maps are not applied to the same set of states. We're not working in the same Hilbert space, okay? In the perspectival approach, or the foundational approach, the quantum reference frame transformations are applied to kinematical states, okay? In particular, these kinematical states are of the form E for my frame and some quantum state for my other frames possibly, and some system. We call these states alignable states. And they live in this kinematical Hilbert space. So we have just a tensor product of Rj and the system. Okay, so nothing has happened here. This is still sort of the perspective from outside, but we're not describing the frame. Okay. In the perspective-neutral approach, we have to do an additional step. The transformations are applied to states in the physical system Hilbert space. So the first thing that we did is we took this kinematical information, we highly entangled it. There are now all of these copies there present, and now we reduce in a way. And this reduction as in the physical Hilbert space is already a lot smaller than the kinematical Hilbert space. If you look at the dimension, and in this S3 example at the bottom of the notes, there's a concrete formula, and you will see how dramatically the size of the Hilbert space, in fact, reduces when you go to the physical one. And now you have this nice feature, I will actually show it here in this triangle picture, that in the perspective-neutral approach, these Hilbert spaces are of the same size. They have the same dimension. Whereas this one right here is in general a lot bigger. Okay? Now, because we applied this projection right here, we're now in the smaller Hilbert space, and now the map that we construct here is mapping between isomorphic Hilbert spaces. Okay? And so this is why we can make it invertible, and if we compose these two maps, it's going to give us a unitary. It's precisely in the case of ideal quantum reference frames where this projector doesn't do much. And in fact, this Hilbert space is still isomorphic to this one. And that is precisely why we can, for ideal frames, apply this map directly here, and this map directly here, and then we can also draw the triangle here, and it's fine. Okay? Does that sort of answer your question? Or does it at least give an intuition?
Yeah, I'm still wondering, because it seems that when you apply this Hamette and pick out some orientation, how can you recover the orientation independent description?
Very good. So that I didn't actually answer, so let's go to where I wrote down the inverse here. Here I actually write down the inverse of this Schrödinger reduction map. So it's true that if we are already in some orientation and now I were to forget where my frame is relative to some external structure, there's no way for me to go back. Okay? the first thing that I do is that I reattach this G. Okay, now you can ask, how do I know what G is? But in fact, it's even the Hilbert space that's still marked by G. So depending on what G I conditioned on or what time of my clock I conditioned on, I'm in a very particular subspace of my physical Hilbert space. And now what I do is I reattach it and I re-coherent average. Okay, so this is what this pi phys here does. Or if you want it here written out more explicitly, I attach some state G on my frame, or actually, I think this should be G dash, because I need to now average over all G dashes, and that's how I reconstruct this very highly entangled state. Okay, and now I have all of my copies again, and again the freedom to now descend into some other term of this very long superposition. Yeah? Okay, good. I guess I don't have much time left.
I mean, you can manage it as you want.
Okay, so this is actually sort of the last thing that I really wanted to talk about. Let's see if we can make sense of what non-ideal frames could be more generally. Okay, this is a non-exhaustive list. I'm not saying that there aren't other really good ideas out there of people trying to make sense of non-ideal frames. So the first one that the explicit one that we just saw here is the one using coherent state systems. And you might have seen that I called them complete quantum reference frames, but I never explained why I called them complete as opposed to incomplete. And that is that for these complete quantum reference frames, and this is going to reply to your question, the group is taken to act regularly on the CSS. Now, regular action is not the same as regular representation. These two are easily confused. So we still have some unitary representation, but the action of the group is both free and transitive. Okay, what do these two properties mean? The free action of the group means that I map from one point in the configuration space to any other point in the configuration space in a unique manner. Okay? There are no two group elements which take me from one point to the other point. Mathematically speaking, this means that if I map from X to X again by some group element, it must be the identity. Okay? That's why it says this right here. What this means concretely is that there are no additional symmetries. There are no two transformations which have the same action on the configuration space. If this is the case, then we have so-called isotropy subgroups or stabilizer subgroups. They are additional symmetries that my system carries. I'm going to give an example in a minute. But we call it complete in this case because if we take all of these frame orientation states G, they can be used to completely parameterize the G orbits in the Hilbert space. Okay, so if we go back to this example that I made a few minutes ago, where we had this sort of two-sphere and the particle on it, you will actually see that in this case, if I take rotations and I take one particle on the ball and I want to, for instance, map to the North Pole, you will immediately see that there are not just one rotation or two rotations, there's an entire subgroup of rotations which will take any point to the North Pole. So the group is SO3, but the subgroup is U1. Okay, so that is an additional, what we call stabilizer group or isotropy group that this would carry. So that would not be a complete frame. And in fact, that would be an incomplete one where our stabilizer group is non-trivial. What is a stabilizer group more rigorously? It is any element of the original group such that the projector on this group element is the same as the projector on the trivial element. Okay? So in this example that I just made, the G group would be SO3 and H would be U1. Or if you think more visually, like me, you would take your entire configuration space, you divide it into orbits, where any point here is related to any other point by a symmetry transformation. But now they're not just related by symmetry transformation under G, you also have this subgroup H now, such that any point that is related to another by some H acting on it is fully indistinguishable. They're the same configuration space point. What this means is the North Pole is the same point that I map to from this state and with this transformation and with this transformation. So in this sense, all these points are identified with one another. Okay, this is very abstract, but what this means for our frame is that it's like taking a clock that is not on the real line, but it's a periodic clock that shows the same time every 12 hours. Now, you cannot make a difference between the clock showing 3 p.m. today and 3 p.m. tomorrow and 3 p.m. in 2 days. but your system is obviously evolving still under time evolutions. So what this means is that you have an additional symmetry on your clock, which makes it impossible to resolve certain properties on your system. How do we express this mathematically? We look at the observables on your system, which would be Fs. Now R is your clock, and normally we would just have this G-twirl, so just this integral over R, but now we have this subgroup. And the subgroup H here, we can separate this out in the integral, and what we will find is that any two observables on your system that only differ by some change in H, so where here the integral over H is the same, I will not be able to resolve them. Okay? So in this sense, because I take my system and I couple the clock to it, but the clock has extra symmetries, I now need to wash over this smaller H subgroup, and I will sort of wash out the properties of the system, even though the system never had this periodic property in the first place. Okay? You can read much more about this in the paper, and I'm also happy to answer questions about this later on. Just to finish the classification, of course, if you can look at incomplete quantum reference frames, which have transitive action but not free action, you can also look at frames that in principle have free action but not transitive action. And just for completeness, they are called overcomplete, but no one has really looked at them because there's not much physical motivation to look at them, for now. Then I also do want to mention that we don't just have to think about sort of different properties of the group action, we can also just change what groups we look at. And in fact, we can look at quantum reference frames based on quantum groups. Those are the ones that are not treated in this paper that these notes are based on. And I give you here one reference, which is a paper by Flaminia from quite recently, where they look at quantum groups, and I think quantum Galilei groups. Yes. Okay. Good. And again, this is not an exhaustive list of different types of non-ideal frames. People are thinking of other restrictions, of restricting the resources that a quantum frame has, and then we have to see how these new other types of non-ideal frames fit within this classification. But these are things that we're still sort of thinking about. Okay. In the remainder of these notes, you can go through this example of S3, and I'm trying to construct the physical Hilbert space and the relational states and so on, and you can look at this, and if you have questions, I'm very happy to answer them today or tomorrow. But this concludes the non-ideal case. Thank you.
Yes. Are all the results that you showed earlier valid for all three categories of reference frames that you presented?
No, so what I constructed here with you now
For the perspective neutral approach, always.
is the, sorry,
Because, for example, for the incomplete frames...
is the complete ones.
Is it?
So the coherent state systems reference frames, we assume them to be complete frames. In addition, you can also take some non-trivial stabilizer group, and this still works with these coherent state systems. But that's it.
Maybe a more specific question. Is the symmetry reduction map unitary if you have incomplete QRFs?
Yes.
Yeah.
Yeah.
So all the main results of
Right,
this
yes,
paper
yeah,
holds?
yeah.
Okay. Yeah.
There's another question over there.
Does it work?
Yes.
Yeah. I have two questions. First, you said that a quantum reference frame was good or bad according to the representation, and not the seed states. What do you mean by good or bad?
Right. In principle, I need to define what good or bad could mean. And in this paper that I mentioned, we defined whether a frame is a good frame to resolve properties of the system if the state the conditional state of the system, conditioned on the frame being in one orientation, is different from the state of the system if I condition on some other state of the frame. As in, if my particle is here, and I'm describing relative distances of my systems over here, then I can compare the overlap of this quantum state compared with if my particle is right here. And then I take the average over all of the positions of the amplitude squared of this overlap. And so in words, what this means is a good frame is one that induces a lot of asymmetry on the system of interest. So I want the state of my system to be very well distinguishable depending on what state the frame is on.
And second question, you kept making an analogy between the state G of the quantum reference frame and the clock.
Yes.
Is it because the model is one-dimensional, or does it work for space too?
I made this analogy mainly because there's the Page-Wouters framework, where this can be seen as a generalization of Page-Wouters, where the frame is a clock and the variable we're interested in is time. But as I said, this holds for all well-behaved symmetry groups, so you can do this for space as well. So position is one example. You can go to orientations as well. Yeah.
Thank you.
Hello. Yeah. So the example you had where you were trying to encode position into like a qubit reference frame,
Mm-hmm.
and this is not super nice because your resolution is not super good. I was just wondering, are you able to connect this language to if I instead consider the qubit interacting with this position carrying particle, and I consider this quantum channel, and then I can put like information bounds on this channel. Would this be like a similar thing?
Right. We have not looked at interactions between the frame and the system. There is just this common tensor product representation that they carry. But first of all, I did not talk about the dynamics here, but you can, of course, transform your Hamiltonian and so on. But we don't include interactions here. There are some papers in the literature where people have started including interaction between the frame and the system. As far as I know, there are no comments yet on channels carrying information between the two.
Okay, thank you.
Maybe it's a very similar question. I mean, it's related.
Mm-hmm.
So you begin from a tensor product of representations, which means somehow that there's no interaction, or in a way, in your constraint, or in a way, the R and S are independent. But
Yes,
you commented
exactly.
on that this may change in the case of gravity, but I would say, why not to change in more general scenarios where
It doesn't
they
only break
interact?
down in quantum gravity. You can create depending on the form of your constraint operator, it will no longer make sense to have the kinematical tensor product structure on your physical Hilbert space. I would even argue that more generally we should question this assumption, the fact that we still have the same meaning of this tensor product that we had on the kinematical level, and now we use the same on the physical level. And I know that some people are working on this and seeing if we can avoid this assumption. If the constraint has a normal form, I think it's fine, and this is what all of this is built on. But I'm not saying that it will only break down in quantum gravity where we don't have the split property.
Okay.
You can, I believe, write down a constraint of some form where this is already not a good
For
assumption
example,
anymore.
do you agree that in the case of time translations, where your generator is the Hamiltonian, what if you have an interaction between R and S? So this is the simplest
Yes,
example.
but I do know that I think there are some papers by Alex Smith and others where they look at a clock interacting with the system.
Okay.
In the Page-Wouters formalism, but whatever they learn can be applied to this.
Hmm.
So I would refer you to those papers.
Okay, thanks.
Yeah. It's funny how the microphone turns off within a second. I can repeat the question. Mhm.
So, within the framework of resource theories, usually, especially in quantum reference frames resource theories, you also classify how well is the resource, I guess, depending on the symmetry of the reference frame, as you mentioned.
Mhm.
But I wonder if there is any measure that you classifying them, and there are many different ways of classifying it, but I'm not
Mhm.
sure if something like that exists in this framework.
Right. The one study that I'm aware of is this paper right here, where we looked into, we used the resource theory of asymmetry, and then related how much asymmetry the frame induces on the system precisely to the Renyi 2 entanglement entropy that we find in the physical state. So what I'm saying is that you can quantify the entanglement entropy in this state right here. You can characterize it precisely using properties just of the representation. So how many copies of which irrep does it carry, and how large is your Hilbert space? And then you find a precise expression for how much asymmetry this induces. And then you can look at different monotones. And in fact, the reason that we found this one relation is that that is the only one where you can make sense of it as a monotone in resource theory. You can also look at others, as in other quantifiers, but they were not good monotones in this resource theory, and that's why we excluded them. And that's why I make this very general statement of saying the choice of E doesn't make a difference, but I should have added the caveat in a way that can be made sense of in a resource theory. Any more questions?
I have a question. I was thinking of asking it later. Do we have time for that?
Yeah, maybe it would take 5 minutes now and then I can continue.
Yeah, I think next is Flaminia again, right?
Next from you.
Because this concludes the frameworks part. So maybe very quickly.
Very quickly. It's not straightforward for me on this network. It's not straightforward for me why in the perspectival approach you act the transformation on the kinematical state, because in the previous lecture we saw that you act on the reduced perspective, and in a way there isn't such a thing as kinematical. So I think there's some more assumptions around this approach.
Right. So I think to be more precise by what I meant is that for the case of ideal reference frames, the reduced physical system Hilbert space, as we call it, looks just like L2 of R for A and L2 of R for B from the perspective of C. So it's the same as if you just took the kinematical Hilbert space, you forgot about this tensor factor of the reference frame, and it's just the same. Whereas for non-ideal frames, this procedure of reducing first, or removing the redundancy and then reducing into the perspective, you get a smaller Hilbert space that is not just L2 of R for each of the systems you're describing relationally. Okay? So in this sense, the perspectival approach is acting on the kinematical states in the sense of the Hilbert space on which it's acting is isomorphic to just the kinematical Hilbert space of these systems. And you wouldn't have gotten to this very, as in for the case of non-ideal frames, down here in this perspective, the states are still very entangled. You didn't fully get rid of it by just reducing.
Yeah.
And you wouldn't have started with this very entangled state in the perspectival approach.
Yeah. But I think that the point of the perspectival approach is that you don't have anything else. I mean, conceptually, also, it seems contradicting to define the kinematical Hilbert space.
I agree that there are motivations to say that actually we shouldn't care about this, but we should just start in here and then try to make sense of non-ideal frames from here. That's going to require some other techniques in order to still have unitary frame changes, but I'm not saying that that's not possible.